It's the third session today. Funny how I was trying to look for the solution of this frame, but I don't know where it is, and I don't know where I got it from. So I'm just gonna have to do it live, but I don't mind really. Okay, so we have more load this time. So to try to say solve this by using the couple and that kind of stuff may cause some confusion. Okay, but one thing I can tell you right away is that when you see that this frame has the vertical load of 15 tons, to go on and assume that this is 7.5 and this is 7.5, this is wrong. Okay, because it is going to be just like that. If you have 15 like this, it's going to be 7.5 and 7.5. Yes, but in this case you have all sorts of things going on. You have this 6 tons producing the counterclockwise moment, 15 tons moving this way, so it's going to cause clockwise moment as well. So the reactions here will be affected by the moment caused by these two loads. So it's not just straight away equal to half of this load, just like this. No. Okay. So we're just going to have to be careful. But one thing for sure is that you still have one horizontal support. So we can safely say that this is going to be 6 tons. For sure. That's one thing we do know. Okay. And before I do that, let me call this A, B, C, and D. We may try to work cleverly, but I suggest it's not going to be very beneficial in the end. So I'm just going to go ahead and take sigma MA equal to 0. Okay. So my sigma MA equal to 0. Some of you, when you take the moment, will still have to feel your way that, okay, 50 multiplied by 4 here around A. So that's going to be clockwise and so on. So, but to me,
Professor.
Yes.
Your skin is facing.
Oh, really? So you don't see my screen?
I can see example number 5.
I don't get you. Oh, so some. Can you?
Okay.
Okay. So yeah, there's some complaint from the chat as well. Can you see the screen or not?
Yes.
Yes or no? What about? Okay, you can see it now. Okay. Thanks for telling me. Okay, so you can see the reaction 6 tons as well, and you can see sigma
Yes.
0. I don't know why I need to write so far up top like that. It's kind of crazy. So let's do it here to celebrate, the rebirth of the screen. Okay, sigma MA equal to 0. So now I can see right away that, okay, 15 tons multiplied by 4 is going to be the moment caused by this. So let's say I say that one is positive. So 6 tons is going to cause counterclockwise. So it's minus 6 multiplied by the moment arm, that is 5. Okay. And then I am going to go ahead and assume that this, let's call it RD, is going up. So it's going to produce the moment in the same direction as the 6 tons. Okay. So that's minus RD multiplied by 8 equal to 0. Okay. So this is 60. That's 30. So 8 RD is equal to 30. Am I right? So that means RD is equal to 3.75 tons. Am I correct?
Yes, yes, yes.
Okay, so you see, it's not half. It's not 7.5. So RD is, oops, so sorry. Okay, okay, 3.75 tons. Okay, now some of you may be tempted to use sigma Fy equal to 0 to solve for RA right away. Yeah, I think you can do so, but in this case, if you have time, you would rather take sigma MD equal to 0 and see what happens, okay? Because let's say if by any chance, sheer bad luck or whatever, you know, somebody just bumped you while you are pressing your calculator, so you punch the wrong button, you don't know, whatever reason is, that get you the wrong reaction here. If you go ahead and take sigma Fy equal to 0, the rest is completely messed up. So it would be wise to try to take moment again at D and see what happens. Okay. So if I take the moment at D, you know, all this reaction will pass this point. So I have just RD. But now this time I have, that look much like a D. Let me rewrite it. Okay. Now I have 15 multiplied by 4. Now this is going to create the counterclockwise moment, right? Because I take moment at D now. So this is counterclockwise. Now the 6 tons will produce the same direction, you see? Plus 6 multiplied by 5. But I would have to assume that RA now is going up. So right here, RA will produce the clockwise moment. So it's RA multiplied by 8 equal to 0. Okay, so that means now this is 60, this is 30, so it's 90. So it's 8 RA equal to 90. So RA would now be how much? 11.25. Am I right?
Yes.
Yes, okay. So thank you. So you can see that if later on, you know, some would follow me, but only up to this point, they take moment at 2 locations, but then they never check sigma Fy. So what's the point of doing it? So we need to also check our sigma Fy. And in this case, you have 7.75 plus 11.25, which is exactly 15 tons. So you see 15 here and 15 there. So our sigma Fy is also correct. So now we can proceed to cut the free body diagram and make our way through all the members of the frame. Okay. And this is 11.25. Okay. So we can, would you like to begin with a member CD now? Just for the change of the atmosphere. Doesn't hurt, you know. Or would you go for AB? You know what? Let me work on AB and let me work on CD and we finish the BC. How's that? There's no response. So let's go for AB now. Looks ugly. Let's do it again. Okay. I suppose AB looks like this. And we have the reaction, okay, 6 here. And then here is 11.25. Okay, so now this is the forces that we know. I'm gonna change the color for the force that we do not know. It's a blue one. So by inspection, we know that this is another 11.25. Okay, so you can put it in your parentheses and by inspection. Sigma Fy, right, equal to 0. And again, by inspection, you know this is 6. Again, by inspection, sigma fx is equal to 0. Okay. Now you know, again, same situation. Okay, thanks. Just saw the chat. Now we need a moment. And again, that you can see the horizontal forces that form the couple will cause this, will try to move this member counterclockwise. So you need clockwise moment. So for the moment, let's use green. You see better. So by using sigma moment equal to 0, you know that this moment MB is equal to 6 multiplied by the height of the frame, which is 5. Sorry. So it's 30 ton-meter. Okay, so this is 30. All right. So let's skip and work on member CD. 3.25. Okay. You know, generally, actually, I like to draw a roller like this, but it used to get students so confused, like what actually the support is, you know, because I got triangle and a wheel. Actually, it's my roller. Okay. So this is 3 1/4. So we know right away that, yeah, okay. This better be 3 1/4 as well. And this is another lead column, right? And if you are confused by the presence of this 6 tons horizontal load, you can try to draw the free body diagram of the joint, okay? We got the 3.75 here. So I know that, so I use the red color to indicate that this 3.75, I know because it has to be equal and opposite to this axial force, which is written in blue by the end of member CD at C. Okay. So but from this, I also know that this better be 3.75, correct? But wait a minute, this is the joint where we have the external load applied, which is 6 tons. So you better include this 6 ton in the free body diagram. Okay, forgive me for not promptly writing the unit. So from this free body diagram, you also must know that this is going to be 6. Okay, so from this, you can proceed to complete the free body diagram of member BC. Okay, you got 6 here, so you got 6 here. You got this one down, so you got this one up. And on the left end, we get the force from column AB. That 6 to the left, so that one is 6 to the right and 11 1/4. 6 to the right. So you see, oh, 6 to the right, how's that? So our sigma fx is taken care of, right? Nicely done. And 11 1/4 comes here. And you know, this is 15. So when you include the external load here, that is sigma fy taken care of. But wait a minute, you still have the moment coming in from member AB. Don't forget that. So the moment is here. This one is clockwise, so it has to be counterclockwise on this member. So that is the free body diagram of member BC. You can try to take moment at C right away to check whether or not your MC is 0, and it better be. And let's do it now. Sigma MC equal to 0. So you now have 11¼ multiplied by 8, right? Minus 30 minus 15 multiplied by 4. That's 0, folks. Can you check it for me? 60, 90, 80, 90. So that's 0, right?
Yes, ka.
Thank you. 0. So that means we are good to go. We are ready. Our free body diagram is completely correct. So when you know that all your free body diagrams are correct, you can proceed and complete your shear force and bending moment diagram with, relieved mind. Okay. So here again, I'm just making up my mind what color I should use. So let's go with black. Okay, I can draw this like this, turn it upside down. Okay, and now the moment is 30 here. Okay, that one is 6. So let me leave the axial force out. Okay, that one is 6. Okay, so my shear force diagram, it's gonna be my negative shear 6, and then my bending moment diagram is gonna bring down to the negative value, because this one, sign convention is like this, so it's negative moment, so that is 30. Okay, shear force diagram, bending moment diagram. The best way to draw this is that you should always include your unit in tons and bending moment diagram in ton meter. That is the best, the complete diagrams. Okay, now let's say here. Okay, this one again is a lean column. Shear force diagram 0, bending moment diagram 0. Okay, now what is left with this one? Now this is not a regular beam anymore because of the presence of this moment. You can see that now. Okay, this one is fine. You need to include that in your bending moment diagram, correct? So let's complete your shear force diagram first. So this is a regular beam in that sense. 11¼ here. Constant until 15. So it drops down 15 to minus 3¾ This area is positive. This area is negative. Okay. And of course, you guys should know now that this better be 15 to show that there is a sudden change of load at this location. Okay, now move on to bending moment diagram. Now remember that we have 30 ton meter, but if you look at the sign convention that you use, this is negative, right? And this left moment, the green one, is this one. So we begin with negative value. So this here is minus 30. Okay, for that shear force diagram in tons. Okay, now we now know that this at this end moment here must be 0. Otherwise, your free body diagram is wrong. So moment here is 0, you know that in the end, this value better come down to 0. In other words, this area which is the positive area, and this area, which is a negative area, should in the end be equal to 30. So that this minus 30 value will go back up to 0. Okay, so let's do that. This area is 11.25 multiplied by 4, right? So that's 45. Am I right? Nobody's helping me at all. Check 45, right? So minus 30. So that means we have a plus 15 here. Anybody struggle to know how I obtain this 15? Let's put a star with let's not do that. 15 comes from minus 30 plus the area of the shear force diagram, which is 11.25 multiplied by 4. 4 is a half distance of member BC, right? And now this area better be equal to minus 15. Is it 7.35? Yeah, multiplied by 4. So it's minus 15. So in the end, this bending moment diagram comes down to 0. Okay? Is there any question, folks? Oh, quiet. Now, there are two things I need to mention. Generally, this is the point where m equal to 0. This point is important because generally, if you can locate this, it is a favorable point for us to try to connect the members. Okay, thank you. So, no. Question, sorry. So, we would try, if we cannot build the one long member and we need to connect a piece of a structure to form one long member, this is where we want to connect the location where moment is equal to 0. We call this point of inflection. Okay. Now, if there is any point of inflection in your bending moment diagram, you should always locate it. Okay. So if you go back to my description here, see, with every point of inflection, now, you know, long time ago, I used to weigh the points for the calculation of point inflection very, very heavily, like 20%. But I think, you know, I changed that a little bit and I weighed it down to a minimum because it is not generally required of you to be able to do so in the calculation, because you can always ask the computer program to do it. So, however, if you are going to complete your diagrams, you should be able to locate this point. And how you can locate this point should be mentioned in statics or mechanics or materials class. Anyway, if that's not the case, I'm going to tell you how easy that is to locate this. This is where the moment is 0, right? But we don't know where it is. So you need to go back and take a look at this free body diagram here. No, not that far. Okay, this free body diagram. So now, if I want to know where moment is 0, I just need to look at the free body diagram here and cut the diagram somewhere where I assume that moment will be 0. So from that, I can just draw the free body diagram. And at location X, where this moment is 0, now I have 11¼ here as my force, and then I have moment here 30. So I can just cut this 3D diagram and write my equation, write my moment equation. So it's going to be minus 30 plus 11¼ multiplied by x equal to 0. Now you can obtain your x. How much is that? Where's my calculator? Here.
2.67.
Pardon me?
2.67.
2.67. Thank you. Okay, makes sense because this x needs to be less than 4, right? Judging from our bending moment diagram. So yeah, we get 2.67, which is less than 4, so that makes sense. Okay, so our first thing out of the window. The second thing that you guys need to be able to see is from the bending moment diagram. Thanks a lot for the answer from the chat. We need to be able to see how your structure is deformed as well. Okay, from the bending moment diagram, if you can recall the sign convention that you use, that is exactly how your structure is going to deform. It is going to deform exactly like your sign convention. Let me try to find my way back. Okay. Far away. No. Oh, not here. Sorry. Sorry for dragging you around. Okay. So let's do it like this. Okay. This is the beam that I drew a few hours before. This is your sign convention. Let's use a different color. This is your sign convention for positive moment, right? Smiling beam. So you know when you have a positive moment in your beam is going to deform like it is smiling. So it's exactly like your sign convention. Okay. Now for this is the sign convention for your negative moment. Take my eyes off that, so it's go a little bit to the side. Okay, so that's your sign convention for negative moment, and so your beam deforms just like that. And we can do the same with a frame. Now, your ability to predict how your beam or how your structure is going to deform will help you a great deal, because you can, if you see the load, you can always expect how your structure is going to deform, and therefore you can sort of expect or predict what kind of moment you should have. Okay, it is not easy, let's say, to be able to anticipate what's going to happen to the structure, but that is your general target in trying to understand the behavior of the structure. I myself would say, talk to the structure. The senior citizen will know. It's my quote. It does. We have a question. So let me go back here. I just said that, but you perhaps didn't catch it. Not in this. The question is, do we need to know where the point of inflection is, right? It's kind of dangerous to say, do we need to? We don't need to, but if we know where it is useful, because let's say here, this piece is long. Okay, this member is long. It's 8 meters. So let's say if this is a frame in the factory, and it is going to be made of steel, just like the picture that I show you. Generally, steel member is fabricated or manufactured so that each member is only 6 meters long. They can make it longer than that, but it's going to be a problem with readjusting the equipment and especially the transportation. You can make the steel like 20 meters long, but how are you going to transport it? So generally, the typical widely accepted length of one member is 6 meters. So for this, if you are going to construct this, it means that you need 2 pieces, correct? So when you need 2 pieces, you need to make a connection somewhere. And it is going to be most preferable if you can make a connection where the moment is closer to 0. Because if you look at the moment diagram, if you are going to connect this member at this location, it means that your connection must be able to withstand moment that much. So it's a waste of materials. It takes more out of the structure because you want to connect the structure where the force is largest. So that's by any means is not the smartest idea. You would want ideally to connect your members closest to this point of inflection. So if you want to be good engineers, this is what you need to do. And point of inflection will play more important role in the approximation of the structure as well. A senior citizen will be able to tell that, because it is where the moment is 0. So when we face tougher situation, we want to approximate the behavior of our structure. We can assume where this point is and put a hinge in the structure and then start our approximation from that point. So to have some idea where this point is very, very useful, I have to say. Okay, so it's a very good question, you know. So if you can locate that, it would be great. And if the point of inflection exists in your structure and you fail to locate that, you may not get a full score. So it's gonna hurt a little bit, you know. Okay. So where was I before that? Deflection, right? Okay. So let's now that we are here, I already mentioned that. You know, look at this member. You see, this is your bending moment diagram, for example. Okay, so you know your compression is going to be on this side, and you know that your member is being pushed like that. So, okay, what's going to happen? This, I think I need a new page. Maybe this is good enough. Okay, so again, this is your frame. This one is a little bit awkward, but anyway. We have the load here. And from the bending moment diagram, we know. So let's go back again to member AB. This is your bending moment diagram, correct? And this is where your compression is. So you know that your frame here must be bent like this. Okay, so that is how your member AB is going to deform. Compression here, tension outside, And because your moment diagram is like this. So you see, now I know that my member AB is going to be bent like this. So now let's go back to member BC. Now you know you have a bending moment diagram on this side, so compression is underneath again. So you see, from the sign convention, negative moment is like that, right? So we know that because our structure is rigid, this, if this go equal to, let's say, delta, this better go delta as well. So, and it's gonna be curved like this, right? Because of negative moment, so it is going to deform like that. You see? And remember, we have a rigid joint, so that means this angle would have to maintain its 90 degree, just like the origin. And you know what? This better maintain 90 degree as well. And your CD has no moment, so it remains straight. But because this is 90 degrees, so here we go. That is how your frame is going to look like. Okay. So now I am working sort of backwards because I know the moment diagram and I draw the deflected shape according to my moment diagram. Now you need to see this first, I believe, because you don't have enough experience. But you know, civil engineering is some sort of that experience counts a lot. If you see a lot, if you work a lot, you will be able to anticipate what's going to happen. Okay, it doesn't take a genius to do it. You can always collect or accumulate your experience, and one day you're going to become good. Okay, so let's try this one. More challenging. This. Now, you see, that is your bending moment diagram here, right? Compression on this side. But again, you know, because the frame is being pushed from right to left. So again, let's use screen, make it bigger. Your frame is going to move like this. Again, right? Compression on the side of your bending moment diagram. But what about BC? You know, the most fun thing is here. Ooh, now you have the negative and the positive moment. So how is member BC is going to deflect? You know that the negative moment will give you this shape, but the positive will give you this shape, right? So rightly so. And look at this point. This is the point where the curvature changes from negative curvature to positive or vice versa. So that's another important issue of the point of inflection. It's where your curvature changes. Here. So that this is how your member BC is going to deform. Okay. Negative, oops, sorry. Negative, and then at the point of inflection, go positive. Right? And we don't know how D is going to be, but it should be pushed away, but how much we don't know. It's going to look like that. But chances are it should, maybe you don't know. We don't know this distance yet, so it's going to be complicated. But that generally that gives you the idea. Okay, so let's say I am giving you something, a typical frame like this. Instead, I push it from the left. Now, without any calculation, can you use your imagination to try to feel how this frame is going to deform? Why don't you give yourself a good 2 or 3 minutes, and I will draw the deflected shape for you. Come on, let's go. I'll be waiting. I'm giving you guys 2 minutes to use your imagination. No calculation required. Just feel the structure. You know, I just can't see if you guys are working or not. This is not the classroom, but let's hope that you guys are trying, okay? No. What? What? So, you know, let me correct your grammar a little bit while waiting. Necessary is an adjective. So you have to say, is it necessary to know? Okay. Not does it. Okay. So is it necessary? Okay. Beneficial. Yeah, that would be the word. Okay, guys, that's 2 minutes now. So I don't want to drag it on too long because, you know, you may, the class may be too late and you may not be happy. So, okay, you know, because this is a hinge, so it has to rotate. So this load is pushing the frame to the side. So it has to go like this. Right? That's the curvature. So, and then this is a rigid joint, so it has to maintain 90 degrees. This one we have to deform like this. And therefore this distance should be equal to this, for example. And this is a lean column and with the 90 degree intact. That's how it should be. Okay, so you guys got the same picture? Yes or no? So, you know, let's say this is what good engineers should see, because if you see stuff like this, you would know right away, you would be able to anticipate that this column will have moment. This member will always have moment, but this moment right here is 0. Okay, so if you can see that, okay, or make it simpler, let's say a simple case of an overhanging beam. How is this beam going to deform? You just push something down very hard at the end like this. So the only way that this structure can deform is like this, correct? It cannot deform otherwise. And what kind of curve is this? This is a negative curvature, right? So when you see this, you should know right away that your bending moment diagram is going to look like this, simply because your beam will have to deflect that way. So one day, if you practice enough, if you see enough, if you accumulate your experience enough, you will just see it right away. Not loud enough. Okay. Okay. This is, folks, what I call talk to the structure. Feel it. Feel the structure. Feel how it is going to behave. See the load. Feel the structure. Okay. That's it for today. If there is any question, okay, let me stop the record first.
Sorry, Professor.
Okay. You're still we're still recording it. Come on, go ahead.
Okay, sure. Is it necessary to written a sign convention for shear force diagram or bending moment diagram, like to written smiling face is positive?
No need. But you know, it's a bit tricky with the shear force diagram, but bending moment diagram, you should write on the correct side of your member. If you don't say anything, I will have to assume that we all write our bending moment diagram on the compression side.
Okay.
If you draw it on the wrong side, I would have to assume that perhaps you don't know what you're doing.
But it will be good if we can indicate it, right?
It's always good if you can provide enough information for yourself and others, of course.
Okay. Thank you.
Cheers. Okay, let me stop the record now.